Lunar magnetism mystery solved. Ancient bursts, not constant strength for decades, scientists have puzzled over the surprisingly strong magnetic signatures found in lunar rocks collected during the Apollo missions. The Moon, despite being smaller and geologically quieter than Earth, shows evidence of a past magnetic field that was, at times, comparable to our planet's. New research from the University of Oxford suggests this wasn't a sustained force, but rather brief, intense bursts triggered by unique geological events. The sampling bias problem, the core issue. Lunar rocks, particularly those from the dark volcanic plains, mare basalts, consistently displayed high levels of magnetism. This led to the assumption that the Moon once had a stronger, longer-lasting magnetic field than it currently does. However, this conclusion may have been skewed by where the Apollo missions collected samples. The research team found a clear correlation. Rocks with the strongest magnetic readings also had the highest titanium content. Their computer models demonstrated that melting titanium-rich material near the Moon's core mantle boundary could create temporary spikes in magnetic field strength. This process would also produce the titanium-rich lava flows that dominate the mare regions, precisely where Apollo astronauts focused their collections. Our new study suggests that the Apollo samples are biased to extremely rare events that lasted a few thousand years. These have been interpreted as representing 0.5 billion years of lunar history. Claire Nichols, planetary geologist, how it works. Titanium and the lunar dynamo, the key is heat flow. The Moon's core is not entirely molten, but periodic melting of titanium-rich material near the core mantle boundary could briefly increase the heat flow from the core, triggering or enhancing dynamo activity. This dynamo activity is what generates the magnetic field, but in this case, it was short-lived. These bursts of magnetism likely lasted only a few thousand years, a blink of an eye compared to the Moon's 4.5 billion-year lifespan. Why this matters? Understanding planetary evolution, this finding isn't just about the Moon. It highlights how sampling bias can distort our understanding of planetary evolution. If we relied on just 6 landing sites on Earth, we might draw similarly skewed conclusions about our own planet's magnetic history. The Apollo missions, while groundbreaking, may have given us an incomplete picture. The discovery suggests that the Moon's magnetic field wasn't a continuous force, but rather a series of powerful, yet fleeting, events. Looking ahead, Artemis and further exploration, the current study is based on limited samples and relies on assumptions where data is scarce. However, the Artemis missions, planned to return humans to the Moon later this decade, will provide new opportunities to collect more rock samples from diverse locations. This could validate the current hypothesis and reveal further insights into the Moon's early magnetic history. By strategically collecting samples in previously unexplored areas, future missions can help us rewrite the story of the Moon's magnetic past and potentially refine our understanding of planetary magnetism across the solar system.